Before lunch, you had from my colleague Kivansh an overview about the lock-in systems, which is more about detection, and now we will dive in the signal control. So producing high-frequency signal with an AWG to control your MV center. And the Zurich Instruments offer different options for this. One would be, for example, the HDWG, which also comes with a nice counter option, which allow you also to do readout simultaneously, but is not able to reach high frequency just by itself. In this tutorial, we will actually focus on the instrument that you will see on most right of this slide, so the SHF-SG, which stands for Super High Frequency Signal Generator, which is able to go from DC to 8.5 gigahertz, hence being able just by himself to excite most important state of a color center. Now, I don't believe I need to go too much into the details of this. This is just to get a small overview and a reminder about what a typical sequence would be. So when you're working with an MV center, you typically want to optically pump, first of all, the MV center into the ground state. So you will need a laser for spin polarization. And that typically could be just a trigger sent to the device to start running the laser. Then you want to excite in a spin 1 plus minus 1 state using a microwave field. And here is where our signal generator comes into play, is actually this part over here that is particularly relevant for this device. And after it's done that, you optically pump the MV center again, but this time to the electronic excited state, and then you detect the fluorescence. And actually a successful excitation will mean less fluorescence seen by an APD count or counter card to measure, and a counter card actually to measure the fluorescence. Okay, so this is what you want to do for control a color center. Now let's try to see how the SHF-SG can help you with that and how would you do such a thing with this device. So this is a small overview of all the cabling. Again, the important part over here, the connection that you can see at the very bottom is from where the HWG with RF modulated coming out. So it's the part that is going to produce the microwave together with the antenna. In this example, we are actually also showing the possibility of sounding multiple tone if you need. And then the third connection here from the bottom is your marker, which just stand for trigger out in the Zurich Instrument wording. This means that you can control your other device. So for example, different tone of laser or the counter card for starting the acquisition using this marker, and you can use the sequence to synchronize very well when this trigger will arrive together with your signal generator. Sorry, yes. Can I actually just stop the video like this? No? Okay. So can I put it over here?
You can minimize it if you click the little
over here.
Yep,
that's good. Okay, perfect. Thank you. So yeah, absolutely. Okay. What are the positive, the most important thing about this device? I would say there is no need for an IQ mixer calibration. This is something we already said this morning, meaning you can go from DC to 8.5 gigahertz using super double heterodyne. You just need to decide your center frequency and the device take care of the rest. You get out of the box just the frequency that you want. And together you have actually a very high temperature stability and a very nice SFDR spectrum. Okay, so this is very broadly how you would connect this device. But now let's dive a little bit more in what the sequence would look like for such an experiment. Okay. So this is the most simple thing you can do is a CW or DMR, so optical detected magnetic resonance. You're doing, in this case, things continuously, and the goal of this experiment is see to which frequency your MV center is responding the best. So you are changing frequency, and you see exactly when you are getting an excitation. This is very simple to implement, of course. There is also a problem with this, meaning that you will have a broader band, so less sensitivity where exactly this frequency lies. But at the same time, you just need to shine continuously the laser, reading out everything that you need, and just sending out the microwave. So it's also very easy to do. But if you want to increase precision in this regard, you might want to do something else, something pulsed. And here it comes the need of really aligning the pulses and having maximal control on your setup. So in this tutorial, we will use the SHF-QC to replicate a couple of sequences that I will now show. Don't be too worried about the fact that we are changing the device. So the difference between the QC and SG is just the presence of another channel over here. But all the channels for 1 to 6 that you see here on the right are actually exactly the same that you would have on an SG. So this is exactly the same device from this side to the right. Now let's connect the cables in this way, meaning, of course, for my microwave, I will need to use one of these out channel to produce the RF signal. And then I am going to use two other markers for two other channels to send out the trigger, either for the readout or for telling to shine in the laser. Now, for this particular experiment is maybe not so crucial. I could just run this sequence very easily. But then maybe I would like to do something a bit more fancy, so a pulsed ODMR, which means that first we will shine the laser, so we will optically pump. Then we will excite with the microsync signal, and then we will shine the laser again, and at the same time start counting. So sending a trigger to the counter card and ask for see how many fluorescents. So in this case, you are decoupling this excitation from then the measurement itself. This is one possible thing, but then you can even do more complicated experiment in a way. You can do a Rabi, and in this case, you will work at a stable power, so a stable amplitude, and then make your pulse larger and larger. So it is always good to keep track of what parameter you want to sweep, so which parameter you want to change. And then even more, you could get to do a Ramsey, so sending 2 pi half pulses, but then sweeping the distance between these 2 pi half pulses to be sensitive to the T2, and so on and so forth. And you see that you basically would like to have a language that is descriptive and flexible to very, powerfully, and I would say also rapidly implement this experiment. And then, of course, you can have even more. We have unheco, decoupling, other more complex sequence that give you more sensitivity. But here we want to keep the tutorial simpler. So we will try to do the first 3 that I just mentioned. So pulse ODMR, Arabi, and then let's see if we get to go also to the Ramsey. Okay, so this is what we want to do, but how do we want to do it? In this case, we are going to use the new software framework that Zurich Instruments developed. This is called LabOne Q. And this morning, you actually saw an approach that was more UI-like. And it's important to say that you could very well use that if you want. You can use that approach to do everything that I'm going to show you today. But sometimes, again, to be more flexible, one would just like to describe the experiment that you want to do. So describe in a Python language, for example, what he really wants to do, and then just send it to the device. Say, okay, this is my experiment. I want the device to run it. So please take care about all these other details. So sampling rate, exactly how to align all the sample, and so on and so forth. So in LabOne Q, this is an example of a Ramsey. You are reasoning in section. You're building sections which are basically a snippet where you align your pulses. So in a section, whenever at the start of the section, there will be the start of the pulse, and you are able to define different sections and then sort of play Tetris. So move them where you want, try to align them. You can make them play one after the other, all simultaneously. So you define this snapshot to align your pulses, and then you arrange them whenever you want. And you can change things around quite easily. So of course, for the nature of this tutorial, I will have to show quite a lot of code. So I would say, let's go to there then, and let's try to use this language to implement this tree experiment. Let's see how one would do this. So let's start from the end. This is not exactly the result we want to have, but when we were talking about CW, this is what you would see, right? You just basically a single tone being played out, but then let's try to move a little bit on the right. Let's zoom out a little bit. And here, there you go. We are in a pulse sequence now. So you see a microwave coming, and then after sending a trigger to the DAQ, in this case, green at the DAQ, and my orange is the trigger that I got to the laser. And this is, of course, just one part of the sequence. You would like to repeat this again and again at different frequency each time and measuring what is the result, right? So here you see the sequence here repeating over and over again. So the laser shining, then laser stopping, starting the microwave, and then shining the laser again, and at the same time, sending something to the DAQ. Okay, so nice, but how did we get to this? So let's start to dive into the code. One of the most important parts that I was talking about before is the sweep parameter. So which parameter do you want to change between one sequence and the other? In this case, it is the frequency. We want to play pulse at different frequency. So we are creating this parameter called frequency sweep, starting from minus 300 megahertz, stopping to plus 300 megahertz 50 times. So we will have 50 different frequency we start and stop defined by this parameter here. Of course, there is a center frequency. We're not really seeing this right now, but it's more or less at 2.7 gigahertz. So this is actually where you are sweeping, right? So 2.7 minus 300 megahertz plus 300 megahertz. Here I am also defining the pulse length. This is basically for how much time I would like my microwave pulse to run. And finally, I'm using the pulse library, also provided by LabOne Q, in this case, just to create a very simple constant pulse of the length that I choose, and the amplitude is this value over here. Okay, so let's run this. Just a simple reminder of what we want to obtain: shining the laser, play a pulse, and then shining the laser and playing the readout simultaneously. So how do we implement it in this language? First, we define an experiment and we reason in signal. So typically, you don't want so much to reason in a number of channels and so on. You really want to imagine the experiment in an abstract way. And the abstract way is I want a drive, which is what is going to be sent out my microwave signal, and then maybe an acoustic optical modulator. In this case, we're just using a trigger, but another line that takes care of the laser. So the drive line will take care of sending the microwave and the readout, and this other line, IOM, will take care of the laser. Then this experiment, we are calling an instruction a while loop RT. This is just giving us the T0 of the experiment, right? So the experiment will start from here on, and there won't be need communication with the PC won't be needed, right? This is why it's called in real time. And here we also say how much time we want to repeat the experiment, because probably we want to do it multiple times for averaging. And you could also define here, for example, repetition time and other parameters. Now, second is a sweep. So as we say, we want to repeat the experiment for different parameters. So we call a sweep and pass as parameter our frequency sweep that we prepared before. What does this mean? Effectively, it would act as a for loop, right? It sort of means that everything that comes after the sweep, which is over here, is actually going to be repeated one time for each of the quantity in the sweep parameter. So immediately after, we define a section, again, because we want to have a snippet of time that where something happens. In this case, the section alignment is not so important, but what I really want to do is to create a section which has a fixed length, which in this case is the length where I want the trigger, so the gate of the OM to be on. And then I say that in this section, using the syntax, which is basically just passing a Python dictionary, I want the trigger to be on, right? So the trigger of whatever line this OM will turn out to be. Remember that right now we are not really saying anything about the device. This will be a map that comes later. You just want to write your experiment and then maybe later remap it because you have different setup, let's say. Also notice over here, since I know that I will have to do this again, I am giving an alias to this section. I want to call this section AOM. Finally, I reserve the signal. This just means that during this section, this signal IOM cannot be used for anything else. So if I try to do something with it at the same time, this section will be postponed because this signal is reserved. You cannot use it for anything else while this section is running. So this is just to do the first pumping, but then you want to send the microwave signal to excite the MV center. So we call this section manipulation, and we specifically say that we want to play after excitation, as it makes sense. Here, I still reserve the AOM because I don't want any laser to shine at this point, and I am assigning to drive a pulse, which is square pulse. I'm using this instruction called play to send a pulse in this drive line. Notice that here, I am not saying how large the section would be, which will mean that the section will be automatically allocated the time it needs. Effectively, this means that it will be as large as whatever I decided for this square pulse. Then I want to shine the laser again, and since it's exactly the same thing as before, I just say the experiment, hey, remember this section before, this AOM, just add it again, and repeat it. Finally, I want to also play the DIQ trigger, and in this case, I am using the trigger of whatever line I assign to drive. So you see, it's pretty much, again, the same syntax. In this case, I want to play this section after manipulation. And again, I say that the trigger of the drive during this section should be on, and I reserve the drive as before. This is actually not needed for this experiment in this case. It's just something that I had for the tutorial to make some time between the repetition, right? Because you have to imagine that all these things will be repeated, both for different frequency, but also for making the averaging. So I'm just making some artificial distance between all of this. Okay, I define my experiment. Next little details. I want the frequency to change, right? So I am calling a calibration object, which is also something defined in LabOne Q, connected to drive, which means that we will act in whatever line that I will assign later to drive. And what is the trick here? In this calibration, I could put any number, but instead I am putting a sweep parameter. This means that this frequency will change together with the sweep. And effectively, it's following the same thing that the sweep is doing. Almost done. The only thing is I finally want to run this experiment on this device, which means that I have finally to say which line is to which device. So I'm assigning drive. This is again a Python dictionary, assigning drive to something that I call the drive line. And this was done in a previous configuration and is just meaning the channel number 1 of our SHFSG. And the IOM is, in this case, channel 3. Again, these are aliases, but this is what this piece is doing. It's just creating a map between our abstract line and our physical line in the device. Okay. It's all ready. So we call the function that is creating the experiment. We set the calibration that we said we need for the frequency. We set the signal map, which is what I did before. And finally, we can just compile and run the experiment. Okay. For now, I'm not showing it again. I will do it later because I just I showed you the experiment as a very first thing. What I want you to see instead is that even without a device present, I could actually run this same thing in emulation mode. Since I am not really calling a device for now, I could just create the whole experiment and then see, okay, let's see what I would look like if I actually run into a device by calling this plot simulation instruction. So here is really parsing what the instruction of the experiment is and just plotting them using the same time axis and show you at each step what you would see. So this is the very first drive line. So you see it's just the square pulse that is sent to the microwave antenna. And you see that is anticipated by this trigger to the AOM, which is what is activating the laser. And immediately after, it is also played the trigger sent to the DAQ for start the counting. Okay, but sometimes you maybe want to have even a larger overview. And for this, we are defining something called pulse sheet viewer. This is in principle an HTML file, so you can open it with a web browser, but maybe it's even cooler to see now that you can directly run it inside your Jupyter notebook. And this is really a complete overview of what the experiment is doing. You see that you can program your timescale. And if you zoom, you will really see the section as you call them. So let's just zoom in one simple thing. We have a parent section that is above all the rest. We have the excitation. Notice that there is a trigger signed by this T during this excitation section. In that manipulation section, there is a pulse in this drive line playing. And then immediately after, we have another excitation section, again with a trigger. And you see at the very beginning of this excitation section, we also have another trigger for the signal drive playing. And you can really explore your whole experiment and see what is happening at all time. And even better, you can in principle also filter things out and in and really have a complete overview of what the experiment will be doing at each point, both in timing and both in sample measurement. And if you double click, let's say, for example, this, you can even go to signal and see exactly this little square, what is doing. So what kind of signal is playing. So in this case, we just have a square signal. So you see in our IQ pulse viewer, we have the eye playing at maximum amplitude. Okay, so we see how things work. And it was quite overhead, I imagine. So when you see these things for the first time, it's a bit difficult. But this is just to say, once you get the first experiment set up, it's actually very easy to then extend and do something else. So let's try again with a Rabi sequence, for example. So what do you want to do with a Rabi? Is again shining a laser, and pretty much all the rest of the experiments is the same, right? What we want really to change is the microwave part, so how the microwave is being played. And the sweep parameter in this case is how much the pulse is dilating, so how large my window would be. So how do I modify in the previous experiment to do this? Again, I would need a sweep parameter, and in this case, it's no longer the frequency, but how large my pulse is. So I'm doing pretty much the same. I'm going from 0, so no pulse, to a stop of 3 microseconds in 20 steps. I need to define a pulse again. In this case, we keep it simple, and we do again a square pulse. What is maybe interesting to see over here is that we put to this pulse this flag clamp compress. What does it mean? Well, we are doing a quite long sweep, right? And if we want to do it by memory, so basically telling the device to do this thing again and again, which is output at maximum power, we are wasting quite a lot of memory, right? Our device can actually prevent that by just telling it to play the last sample continuously, which means that you are effectively using just a minimal amount of memory to play the waveform. You need to tell the compiler that it can do that, but after you do this, you can do sweep very effectively because essentially you're not really wasting waveform memory. You can do it as long as you want. Okay, so the experiment over here actually looks the same. I won't go to all the details again because they are the same. You see, I'm still calling AOM. I am still having a laser shining at first. I am not changing anything of the experiment that I did before. There is one thing that I'm changing, but just to show you, which is that there are two ways actually to send trigger. This other one that you see was connected to sections, and it has a jitter of a couple of nanoseconds, but you can actually make a trigger which is really synchronized to the sample, so really to a waveform. In this case, the jitter will be in the picosecond region, right? Tens of picoseconds. And this is how you would do it. I am in the trigger section. You see, instead of connecting to the section, I am just playing a dummy pulse and tell this marker, which you see now is connected to the pulse, at which point it should really output the signal sent to the counter card. But this is just to show you that you can do this as well. In principle, I could have left the things the same. So what is really changing about this experiment is just the manipulation part, right? I just want to change how I manipulate with microwave my device. So how does it change? I am now overloading the length of the pulse with the sweep parameter. This may be another important concept. You can always overload parameter of your pulse. And if you overload it with a sweep parameter, it means that at each section, it will be used a different value. So what I would see here, let's first do it in the simulation, actually. So you see, right now I'm not showing the trigger again, but you still have the laser, which is this sandwich over here, right? And you see also that the 2 times where the trigger of the laser is sent, they are getting more distance because they are making automatically space for the microwave to arrive. So here, the microwave is becoming larger and larger, and the 2 triggers sent to the laser are becoming more spread because they need to act immediately after that this pulse arrives. In the pulse sheet viewer, it will look the same. And again, you can actually immediately see that this pulse, just by scrolling, is becoming larger and larger, exactly as the sweep command him to do. And if I go, if I load long enough, it's going to the other average. So now it's going back to 0 and he's doing it again to average the result. So let's also try to see it in the oscilloscope, and I'm going over here. So I need to tell him to wait for a trigger again. Let's do it. Here we go. So we have a pulse coming here for the left, becoming larger and larger, and the 2 triggers sent to the laser are becoming more spread to make space to him, and you have also the trigger sent to the DAQ to activate the counter card. Okay, so I have still 5 minutes, and my original plan, not to be too overwhelmed, is to ask if anybody wants to take a guess of what a Ramsey would look like. It's like 2 lines of code. I can do it myself if you want. So I will start talking. I mean, if somebody knows how to do it, he can raise his hand. Otherwise, I will implement it myself. But again, Ramsey, you still need to see mostly the microwave part, right? So the rest of the experiment will be exactly the same. I want to play 2 pulses this time and add some spread in between.
I think I have a question. So before you were trying to put down
the initial phase, I mean, it depends from the experiment, of course. In this case, you are not resetting it for a Ramsey because it just basically what the phase is correct is just being dominated by the first pulse, right? I mean, you could choose to reset it if you want, but in this case, we are just keeping the same phase. I mean, you can do both in principle. You have power to command this as well. Okay, so how it would look like, again, sweep parameter. So this time We did frequency, we did length, and in this case is also length, but of waiting, so space in between pulses. I am also making it as a function over here. If we go and see how the experiment looks like, it's still the same, because again, we just need to touch the manipulation part. Now, what to put here? Nobody wants to guess this, so I can just do it myself. I do a play, right? So what signal is again in the drive line? And what kind of pulse? I am just doing an X90 in this case. Okay, so these I will need later. Then I want to delay, right? I want to call a delay instruction because I want to wait some time. The signal where this delay is playing is still drive, because I don't want drive pulse to do anything while this delay is happening. This is how I am making it happening. And the time now is going to be my sweep parameter, right? So this is something that we created before. We wait for a time that depends on which point of the sweep you are. Then after I delayed for some unfixed time, I play the same pulse again the X90. And this is how you do a Ramsey, right? There are 3 lines of code. You just need to add them on the top of the experiment that you did before. Okay, so let's try to do same thing that we did before. First of all, plotting the simulation. Does everything looks good to you? These 2 pulses start very close, and then in each step, they're becoming more and more spread. And this, by the way, is because I am always choosing a cycling average. I could choose to do sequential, and in this case, you would see the pulses always connected, right? But it's better to show to an audience to do it cyclic in this case. Pulse sheet viewer, I will see exactly the same. So if I will zoom out, we see things become more spread and spread, and then at some point, they start to be connected again. Last step, we go to our scope. We put it in single. And let's run the experiment again. There you go. So here you are seeing things a little bit in the middle, but you can see, well, I'm actually counting from the runtime, but they become more and more spread, right? So here they're coming close, here they have more distance, and things go on and on. Okay, so we saw the 3 experiments that we said originally. We have still a couple of minutes. If you already have some questions, feel free to ask them right now. Otherwise, there will be a Q&A after where you come, and we can play with this together as well. We don't even need the instrument because, again, we can just look at the simulation if you want.